seems we are live now. Apparently, I can see it on my second PC. All right, perfect. So hi guys, we're gonna wait for a couple of minutes for more people to come. So for this new session of Coffee Break with Eddyfi, my name is Frederick Ravali. So I'm checking my second PC just to check if some people, I'm gonna wait for more people. So let's wait for like 2-3 minutes, and then we'll start. So just a few things. If you are actually watching right now on YouTube and you are not logged onto your YouTube account or your Gmail account, you are not going to be able to chat. So if you want to be able to ask some questions, just subscribe to our YouTube channel or just have a Gmail account. It's pretty quick, and then you will be able to ask questions. Of course, if the video is going to be online on our YouTube channel, so you will always be able to ask questions or send me an email on my personal email. So that's no problem. Still gonna wait a couple of seconds. So if you see me turning my head, it's just because I have a second laptop with what's happening on YouTube on the chat. Let's wait a couple. It's like another 30 seconds. Okay. Okay, you know what? So let's start. So again, thanks for those who are attending. So we are in my house having coffee. So I hope you have your mug. I'm having probably my third or fourth coffee of the day. This is my apartment. You can see that I have right here like a nice deco in my desk. Today we're going to talk about analysis with a new feature of Capture 3.1. So again, I just want to clear some things. There is a 30-second delay between me talking or moving anything on the screen and you seeing it actually in YouTube Live. So bear with me if if you ask questions and I don't answer them right away. I think I'm going to answer them probably at the end of the meeting. Okay, so let's jump right in. Okay, we're going to talk about analysis today, and to illustrate that, I'm going to use a weld inspection that we have done with TFM. So here is the interface when you start the file. So we have here the TFM image with the A-scan. So right now for my analysis file, I have 4 different tabs with different views like C-scan, some echo dynamics, some side views, some D-scan. Also have a 3D view right here that I will be using just after. But before, I just want to describe a little bit the configuration that I'm using. And for that, I'm just going to use another capture. So this is the configuration. I'm looking at a 25mm V-weld, so 1 inch. I'm using 64 element, 5 MHz, 0.6mm pitch, so very typical. And we are using shear 55 shear wave wedge, and we can see that it was calibrated. So we did a wedge delay calibration. So here we are in the TFM. We can see that we did our amplitude fidelity. I'm just gonna up. So what the inspection was, so here is our probe, 64 element. Here's our TFM area. You can see that we did a TFM which is 40 millimeter by 50 millimeter. So we have the first leg and the second leg. So instead of doing a full matrix capture, we did something on what we call the plane wave imaging. So the emission is a sectoral scan, but only with a few angles. And we do a TFM afterward to be fast. So if you want more information, you can go here on our website, so the eddyfi.com webpage, and right here on the side you have something called blog. So you can see a lot of the blogs that are being posted by myself or a lot of my colleagues. And the one that explains plane wave imaging is this one, increasing productivity. So you just have to click on it, and you will have more explanation about what plane wave imaging is all about. So this way you can understand what the inspection was. But really, so here for this TFM we have about 123,000 pixels, and we are able to reach a speed of 83 millimeters per second. So taking a data point every 1 millimeter. So that's kind of the reason why we are using the plane wave imaging, is to be able to be really fast. And to be able to have, a productivity compatible with the inspection that operators really want to have. Okay, so let's go back to the analysis of that file. So right now, the well that we inspected has 3 indications. You can see one right here, which is lack of sidewall fusion. You can see another one right here, which is root crack, tip corner echo, and tip diffraction. And you can see right here, kind of weak, but we have a toe crack right here. So we're going to do the analysis of these 3 defects using different techniques. But first, I just want to go right here and show the new banner of indicators. So right now we have up to 8 indicators that we can display at the same time. Before we used to have only 4. Of course, when you are using the Mantis or the Gecko, you are limited to 4 indicators at the same time, but you can toggle between the 8. You can completely customize all these indicators. For example, here, if I look at amplitude, with amplitude I can display the amplitude in percentage of dB. I can display the amplitude with respect to the TCG, the equivalent reflector size. I can display an alarm and so on. For the cursors, I can display the scan position, the index position, the well center line, a lot of information. And we also have some statistics with the miss data rate. So when you're inspecting in real time, you see how many, the percentage of frame that you actually missed, the material loss in percentage of millimeters, and all kind of information for corrosion mapping. You can save your banner of indicators, and have some different banners depending on your application. We also have some templates. So right now I'm using the world reading template that has some of the most common indicators. Okay. Now we're going to talk about the new feature, which is called auto sizing. So here at the bottom left, we have a new button which is called sizing, and you have this auto sizing feature. So as the name implies, basically the auto sizing is going to try to give you automatically the length and height and other parameters of defects. And for that we can do that 2 ways. We can size the indication based on the maximum amplitude. So basically we're going to look at the maximum amplitude on the defect, and we're going to do a -6 dB drop along the length, for example, and a -2 dB drop along the height. Or we can use reference amplitude, for example, like 3 millimeter side ray hole, which is something very typical that we see with the ISO standard, for example. For now, I'm going to use the maximum amplitude, and I'm going to put -6 and -6 dB for my lack of sidewall fusion. The reason I'm doing that is we are doing TFM, so my focal spot, so the size of my beam close to my defect is really small. So I have a beam which is smaller than my defect. So the minus 6 dB is actually not that bad to evaluate the size of my defect. So I'm just going to select my tool, and here I can see that auto sizing created a box around it, around my indication on the C-scan and on the T-scan, with the size of the indication based on the minus 6 dB criteria that I have decided. So I'm just going to take a screenshot. So I'm going to add a screenshot to the indication number 1. I mean, so far I only have one. And if I go back to sizing and here to the table of indication, I can see that I have up in my table of indication my first indication with some information. Again, I can completely customize all this information. I just click on table setup and I see again all the features I had before. But here I'm just going to load the template, weld. Okay, and I have the most characteristic parameters of the indication, like the scan start, the length of the defect, the weld center line, and so on. The angle is mostly for phased array, so I'm just going to select the angle and remove it because I don't really have an angle. Okay, so I can see I'd use the auto sizing feature with the minus 6 dB and minus 6 dB. I have the screenshot I have taken, and by now I know this is a flow. I'm going to say it's a lack of side LOF, lack of sidewall fusion. For the acceptance, so this is going to be for the operator to decide based on standard. So for example, if I use the ISO standard for phased array, looking at the thickness, so right now my defect is about 37 millimeter. I'm looking at the sample that's 25 millimeter. The amplitude of my defect is 2 dB above my reference, so this defect is definitively a reject. Okay, so I have, I'm going to unzoom, I'm going to zoom out. Okay, so here I have just did a characterization of my first defect. For the second defect, which we have right here, it's root crack. I'm going to use a more traditional way of doing it. I'm going to use different cursors. And we can see that as I move, I have different tip diffraction. Okay, so I'm going to zoom right here. I'm going to have 3 cursors. So now I have 3 cursors. The orange one is my data cursor, the blue one is my reference cursor, and the green one is my measurement cursor. So what I'm going to do is because I have tip diffraction, and when I have tip diffraction, that's what you want to do. That's what you want to use when you do sizing. So I'm going to look for the maximum right here of my tip diffraction. I can see right now that I have a little bit of saturation, so I'm just going to change the dynamic range. On the Gecko and the Mantis, we can record data on 16-bit, so that means we have 800% dynamic range. So right here, I can just change on 200%. Okay. So I'm going to look for the maximum of my echo right here. So this is the maximum of my tip diffraction. So right now my data cursor is positioned on the maximum of my tip diffraction. So I can just select the tool right here, the D, and I can bring the reference cursor to the blue one to the position of the orange. So right now they are superimposed. Now I'm going to look for the maximum of that echo right here. So I'm moving this one, and I'm going to look for the maximum right here of the corner echo. It's kind of right here. So I'm going to do the same, but this time I'm going to select my T-scan, and I'm going to move the measurement cursor for the depth and for the shot. So I have done my sizing on along the height. Now I want to do along the length. So I'm zooming on my C-scan. So here I see my corner echo, here I see my tip diffraction, and I'm going to look for a 14 dB drop compared to my maximum. If you look at the ISO standard, when you are doing like sizing along the length, based on a different acceptance level, so if it's the acceptance level number 2, that's a 14 dB. If it's a acceptance level number 3, it's a 10 dB. I'm just going to choose a 14 dB. I'm going to change my scale right here, which is in percentage. I'm going to change it to dB. Okay, right here. I'm going to look for my maximum, which is kind of right here. I'm going to bring my measurement cursor. And I'm going to select my, amplitude. I'm going to select my measurement. I'm going to look for 14 dB. So here we see that we have a 14 dB drop between my measurement cursor, my reference cursor, and my measurement cursor. So now what I can do is I can select my data cursor and look for my 14 dB drop in amplitude, so which is right here. I bring my reference cursor, so I have my blue cursor right now. I go the other way and I look for my other 14 dB drop. And I bring my measurement cursor. Of course, if you are used to use a 6 dB drop, you can use a 6 dB drop, you can do whatever you want. Now we have this new icon right here into the table. So I can just click on it, and you can see that I added a cursor right here, and automatically now in my sizing, I have a new indication. Again, with the length and all the values. I could have taken an image. Right now, my flow, I know this is a root crack. Okay. I forgot to take my picture, so I can always take my picture after, and I can add it to the indication number 2. And right now, I have it into my indication number 2. All right. Okay, so now I have my last defect, which is the toe crack. I'm going to bring my dynamic range back to 100%. And right now we're going to do a little bit of combination of the two sizing technique. So I'm going to use the auto sizing feature, but instead of using the maximum amplitude, I'm going to use the reference amplitude. So remember, here, when I did my inspection, I did a TCG using like 3mm salvage hole. So this is my reference level. So based on the international standard, if I look for sizing for the acceptance level 2, sorry, pardon my French, as we say, I'm going to put a 14 dB, and here it doesn't really matter for the height, I'm just going to put 6 dB. So what does that mean? That means that instead of using the maximum amplitude of my toe crack, now Capture is going to look for a 14 dB drop compared to my amplitude reference of 80%. So I'm still going to use the auto sizing feature. I'm going to zoom on it. I'm going to zoom on it right here. So we see that the length is measured properly at with a 14 dB drop. But we can see here that I'm going to increase my soft gain a little bit. We can see that the sizing for the height is not really good. This is a crack, so I have a corner echo, I have some diffraction echo. So if I really want to size it, I have to modify my box right here. So if I look right here, so this is the A-scan, the corresponding A-scan to the column. We can see that probably the tip of my defect is the one kind of right here. I can look for I can look for a maximum right here. So this is probably kind of the maximum of my defect. So if I want to select it, I'm going to bring my blue cursor and I'm going to adjust my box to the maximum right here. So this way the box is measuring completely the height of my defect. the bottom of my defect is obviously the maximum, which is indicated by here. So the same way, I'm gonna adjust it this way. So this way, I have sized manually using the tip diffraction echoes the height of the defect, and I've used the auto sizing with the minus 14 dB to size the length of the defect. I'm going to take a screenshot, add it to the feature number 3, and now I can go back and zoom, and I can go look at my table. So now I have my 3 indications with the 3 pictures. This is also a flaw. This is a toe crack. Oops, sorry, I closed it. Essentially, based on standards, any cracks is typically rejected, especially when we look at the length and the amplitude with respect to the TCG. Okay, so that's kind of the different ways of sizing a defect using the new feature of Capture 3.1. We have also a new feature with that version, which is the possibility of exporting data in 3D. Before, we always had the possibility to export the T-scan or the sectorial scan into the 3D view. And for example, right now I can see my toe crack right here. If I move this way, I can see my lack of sidewall fusion. If I look here, I can see my wood crack. So with the new version, we actually have a new icon right here, which is called 3D. And if you click on it, you essentially export in 3D all the data of your inspection. So you can see here my wood crack, my lack of sidewall fusion, and my toe crack. I'm going to remove my T-scan. I can edit the dynamic range. So right now I'm looking at the full dynamic range, but let's say, for example, I only want to look at, you see I adjusted on my C-scan the dynamic range. I also adjusted it on the 3D view. I can also add more soft gain if I want. Capture is recomputing. And now I have more gain on my image. Of course, I can take a screenshot of that image as well. Instead of adding into the indication, I'm going to add it here. I'm going to call it 3D, for example. And I will add it directly to the report. Okay, so I have done my complete analysis. I've done the auto sizing of my 3 defects. I have done like the 3D export, and right now I can go look into the report. So Capture is creating the report with the logo. Of course, you can have your own logo. You can have all the information about the inspection that you want. You can have the specimen, the transducer that reminds you as well that if it was calibrated or not. The ultrasonic data, so here this is all the parameters of the TCG. So of course, because we have a lot of columns, that's a lot of parameters. So for now, I'm just gonna only show the inspection data. So in this inspection data, we have the screenshot of the 3D part. We have our table of indication. So we have the number 1 indication, which was the lack of sidewall fusion, with a screenshot and all the information that were into the table of indication. So with the scan start, the length, the criteria that we used, if we rejected the defect, the comment on it. Same thing for indication number 2. So this one we use a manual sizing, and indication number 3. So we did a little bit of a mix between between the auto sizing and the manual sizing. Of course, I can always add more comments at the end. Bad weld that will be added at the end. We can then save the report. So if we do click on the save icon right here, we are going to save it into the same folder as the data. We can also export the report two ways. We used to be able to only export as a PDF, so I'm going to select my hard drive right here. But now we can also export as an Excel file. So I'm going to export it as an Excel, and I'm going to create the report. If I go to my D drive, okay, so now we have our inspection report as an Excel file with all the pictures, our table of indication, and basically you can edit everything using a typical like Excel and add all your information as you want. So it's a little bit more customizable than before. All right. Now I'm going to go back here. I'm going to go back to this. So if you have some questions, let me look into the feed. I have a lot of colleagues saying things. But if you have any questions, you can ask them in the chat, and I'll be more than happy to answer them. Again, that's our second session of Coffee Break with Eddyfi. My colleague Liam from Inuktun did one on Monday. We're going to try to do a lot more of those, and take I wouldn't say advantage, but use our confinement time to try to be creative and show you like some of the different like business unit what they can do. Also, if you go into our page, web page, on top right here, there is something called Eddyfi Academy. So I know some of my colleagues want me to mention that. So this is something that we are starting also as well. Is you can register and have some free courses about different techniques. So at the moment, you have introduction to TFM. You have how to do a setup with capture, something about my colleagues from Eddyfi, from the Eddy Current, and also the new PAM scan. There will be more in the future, so please check sometime if you want to have some nice free insight about different technology. Also please subscribe to our YouTube channel. You will be informed about the next Coffee Break with Eddyfi, and if you don't have any questions, I'm just gonna hang up. Oh, I just have a question. Sorry, I'm looking on my other PC. So I have a question about, can one create their own table of indication? Yes, someone can create their own table of indication. If I go back right here, so I have my table of indication with the different features. I can completely customize it. So if I want to remove a lot of the information and just have that much information, I can have that much information. I can save it. I can call it, I don't know, Fred, and then I can always recall into the characteristic the new one. So you can create your own table of indication and customize it as much as you want. By default, we have three. We have the corrosion one, the Toft one, and the weld one. With some of the parameters we think are the most useful for you guys. Of course, you might have a different opinion, and you can change them, as much as you want, and you can really customize and the way you want. So for the table of indication and as well for the banner, you can really customize them. Another question. Okay, so love the 3D Explorer, thanks. Are there any other impressive features or included with the advanced analysis tool? Today I was using weld inspection, but with the 3.1 version, we have different features as well. We have stitching for corrosion mapping. So if you go into our blog, there was a blog about the new analysis tool in Capture. This is just a blog that summarizes like the new features that came with it. We basically have the stitching for C-scan for corrosion mapping. So this is one of the nice features as well. When you have done like different bands of corrosion, like this one for example, you select your files and then you can create one large file for your corrosion mapping. And this is the type of export you can get in 3D for like corrosion, for example, on the background. So this is one of the features that we also added to this like analysis tools. Yeah, other question. Are the advanced analysis included with the equipment? Yes, anybody purchasing a Gecko today will have these tools embedded into the equipment on the Gecko. Of course, if you want a version for your PC, that's the version that you will need to purchase. But if you purchase a Gecko today, you will have all these features and you can do the analysis on your Gecko exactly the same way I just did it. So no extra things required. This is all on the equipment. Well, question that. Question about plane wave imaging for weld inspection versus conventional PA. Okay, so that's not analysis, but that's an interesting question. Like I mentioned here, I'm going back here. So here we instead of doing a regular TFM from a full matrix capture, which is like the most typical way of doing a TFM. I mentioned at the beginning, for those who missed the beginning of the session, that we are doing something called a plane wave imaging. And again, if you want more information, you can find more information on the blog on this one. Increase productivity. Check this page. There is a lot of information from all the business units. So the advantage here of plane wave imaging with respect compared to PAUT, I will say, is that the reconstruction, we focus everywhere. So we have maximum spatial resolution everywhere inside the area, the region of interest, compared to PAUT. PAUT, you will do a very similar sectoral scan, 35 to maybe 70, 75, and you will either focus or not focus the energy somewhere, and while you will be focusing the energy, you will have more information, more sensitivity, but of course, outside of this focus area, you might be losing some sensitivity. So here with the plane wave imaging combined with the TFM, you don't really have to worry about where to focus the energy, because the TFM does that for you. So you will have minimum spatial resolution everywhere inside that area, and that allows us to obtain this focus everywhere and have this nice tip diffraction. Also, let me kind of decrease the gain a little bit. I forgot to mention something. Here, let me remove some of the cursors. It's a lot of them. So here we have our lack of servo fusion. I guess I forgot to change the offset. I can change the offset to align it. Forgot to mention also with 3.1 you can change edit the thickness after the fact. You can also change the color of your overlay if you want to have overlay that's red. But really having this plane wave imaging combined with the TFM allows you to have maximum sensibility everywhere. So you're going to have like a lot of you're going to be sensitive to the tip diffraction. If I go back to our toe crack right here, let me up. you can see actually, this is interesting. You can see here the corner echo. You can see a tip diffraction, and you can see another one. The two of them are very close to each other, but because you focus at both locations, you are using a full 64 lemon aperture. You are able to distinguish between the two tip diffraction. So actually the crack, the way it's propagating right here, it's actually like growing like this, and then after it's actually following the bevel, essentially. This is what's happening. So this is kind of an interesting position. Yeah, another question. I'm going to go back to here. I said it a little bit earlier. But plane wave imaging, of course, is all about speed compared to full matrix capture and TFM. So right now, using 123,000 pixels, using my PWI, I'm able to reach about 83 millimeters per second. You see I'm using 123,000 pixels, full 64 element aperture, so I'm not using 32 element, I'm using the full 32 element. But because I'm firing only a couple of times, instead of firing 64 times with a full matrix capture, I'm able to have this increase in productivity by firing less. So that's why I'm able to reach this 83 millimeters per second. And again, this is for a data point acquired every 1 millimeter. I'm not making a data point every 2 millimeters or so. Another thing about PWI, because we fire all the elements, we send more energy as we fire. So we have we can penetrate more thicker material or more attenuated material if you're looking at HDPE, for example, type material compared to a full matrix capture. But again, like I don't want to necessarily oppose PWI, FMC, and PAUT. All the techniques have some advantages and pros and cons. I like to do this analogy all the time, but the gecko is like a Swiss Army knife. You have your screwdriver, you have your knife, you have your screwdriver. Very important these days. Well, the gecko is kind of the same. Sometimes you're going to use the Toft, sometimes you're going to use the PAUT, sometimes you combine obviously the two. Sometimes you're going to do TFM, sometimes you might be able to do plane wave imaging. You just pick and choose. We just give you the tools, and you guys choose what tool is best for your application. And I think that's it. Trying to go back to the question. Let me try to see if I have more questions. No, actually I don't have more questions. All right. So again, thank you guys for being here, for attending this session of Coffee Break. There will be more in the future. So I know my colleagues from marketing want to have put more information out there during those times and in the future. So next week is probably going to be my colleague Guillaume, who's going to talk about I think DLA and using 2 times 64 elements about stainless steel. But you will be informed, the usual LinkedIn and other social media about the next coffee break. Again, this video is going to be available on YouTube, on our YouTube channel. Please also subscribe to the YouTube channel so you can get information about the next coffee break. Yes, if you have some questions, you can send me some emails to my email address, which is freverdy@eddyfi.com. So that's freverdy@eddyfi.com. I don't even know how to spell my name anymore these days. So again, thanks for sharing a coffee with me, and please come back for the next session of Coffee Break. Thank you guys, and stay safe in those days. All right, take care. Bye.